What's up, peeps? It's Kenya here, indie scientist back, and today we're watching a video from PBS Space Time that says the universe is racing apart. We might finally know why. It's about dark energy. Wanted to get into it because I have some ideas on it, so let's watch it.
2014, the pale electromagnetic ghosts of an ancient exploded star barely grazed the camera of the Hubble Space Telescope. 4 points of dim light revealing the same supernova, framing the galaxies whose gravitational field had bent this light to us. After a 9.3 billion year journey, the images arrived in rapid succession. But other longer paths wove the space-time contortions of the surrounding galaxy cluster. Astronomers spun up their
Really
models
interesting.
and predicted a single explosive encore the following year. They waited, they prepared the Hubble.
Wasn't going to stop it, but I was going to say, one thing I think is, I think quantum physics is almost a similar effect. I This is obviously, us seeing the same thing multiple times because light's being bent on a macro level. But I think in a certain type of way, you're looking at something larger than time, even when you zoom in. But let's just keep watching.
And 12 months later, there it was, the laggard after image of the supernova just as predicted. Ridiculous that we were even able to predict this, but more incredible is its scientific value. In a 1964 paper, Sieur Revsdahl pointed out that the time delay between gravitationally lensed supernova images can give us a way to measure the expansion rate of the whole universe. We've now done that with the eponymous supernova Revsdahl, but we've now also built this up into what may become the most powerful method for unlocking the nature of dark energy. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best
Try
way
to
to
skip this a
encourage
little
YouTube
bit, see
to
if I
share
can.
our are still available. Links in this. To the contrary, which may be why the dark energy has a constant density.
Funnily enough, and a lot of scientists definitely don't agree with this at all. I kind of think dark energy is the same thing as dark matter. I know maybe it doesn't make sense, but that dark energy is what dark matter looks like outside of the galaxy, same force. And I think they might be related to the sixth dimension. That's where I was kind of coming off from this, and so I want to see how it all draws together.
Always the same amount of outward shoving stuff per volume of space. But there's recent evidence to the contrary, which may be why our primary efforts to measure the expansion rate of the universe disagree with each other. Let's review those methods. On the one hand, studying the oldest light in the universe, the cosmic microwave background, the CMB, gives us exquisite information about a time soon after the Big Bang. Combined with our cosmological model, we can predict how fast the universe should be expanding now, and that modern expansion is characterized as the Hubble constant. On the other hand, observations of supernova explosions allow us to track the expansion history in the relatively modern universe. Exploding white dwarf stars, type 1a supernovae, have very predictable intrinsic brightnesses, allowing us to determine distances based on how faint they appear to us, and those distances give us another measure of the Hubble constant, in a sense more directly measuring that modern expansion rate. If our measurements are good and our cosmological model is good, then the CMB and the supernova results should match, but they don't. The supernova program finds an expansion rate a few percent higher than the extrapolation of the CMB measurements. So either the CMB or the supernova result is flawed, or the cosmological model that we use to extrapolate between the two is wrong. This so-called
I also think that at really, really large scales, at like the scale of the universe, this is just my hypothesis, I actually think that there's probably other forces there, so it's not just that, so that, I can't remember which one they said was larger right now, but if the cosmic background radiation is larger, I would imagine that it would be And those forces would be even weaker than expansion, so maybe it wouldn't be by much, but let's see if that has anything to do with anything.
Hubble tension has been lurking around for some years and stubbornly refuses to go away even as we improve our measurements. That hints that we may really need new physics in our cosmological model. For example, the model assumes constant dark energy, but what if dark energy really changes over time? But before we jump to conclusions, it's absolutely
Or
critical
over
that we make
space.
independent measurements of the expansion history. The supernova results are particularly vulnerable to systematic errors because they need to be bootstrapped off a series of distance calibration steps, more room for weak links in the calculation chain. Now, some would say, me included, that one of the most promising independent methods is something called time delay cosmography. This is the method outlined by Sir Rifstal and was applied to the eponymous supernova. But it turns out that we can use a different type of cosmic cataclysm that's actually far brighter and more common than the supernova, the quasar. And the best time delay cosmography has been done with quasars. So I will start by talking about quasars, but supernovae do have a bright future in this field, as we'll see. So a quasar is what you get when a supermassive black hole in the center of a galaxy enters a feeding frenzy, as happens from time to time. Active galactic nucleus is the more general term, and quasars are the bright ones that we care about. So, matter driven into the galactic core is caught in the colossal gravitational field and spirals in to feed the black hole. The gas also generates such prodigious heat on
It's just sort of crazy how, casually we can talk about this stuff like a giant black hole in the center of a galaxy. A giant black. Okay, let's keep going.
its way.
I mean, our brains, can they even comprehend that scale? Like, not really. I think so we're so calm talking about them.
That these accretion disks glow bright enough to be seen across the universe. Quasars are messy eaters. The infalling material comes in fits and bursts, and the bright central region fluctuates wildly. This causes the entire beast to flicker on timescales of hours to months. By itself, a quasar isn't great for measuring distances, but if we introduce a new level of chaos, then the magic happens. In Einstein's universe, light does not travel to us in straight lines. Mass curves space-time, and light is bound to follow those curves. We see the effects of this gravitational lensing everywhere in the universe. Most of the lensing is subtle, manifesting as changes in brightness and warping of shapes, but in rare cases, a gravitational lens is so perfectly situated between us and the distant source that the latter's light follows multiple paths to reach us. We literally see the same object through different paths through space, and that looks like duplications of the source around the lens. This is strong lensing, and strongly lensed quasars are going to become our new cosmic expansion tracker. The 2 or 4 different paths taken by the quasar's light are different lengths, and so the light that we see in each of the images has taken a different amount of time to reach us. So although we're looking at the same quasar in each image, we're looking at the quasar as it was at slightly different times, and this is where the quasar variability comes in. The brightness fluctuations are pretty random, but they still form distinct patterns in the light curve, the plot of brightness over time. If we can record the light curves of different images in one lensed quasar, then we can find where the light curve patterns match up, and that gives us the time difference of the paths for the different images. We call this the time delay. That in turn gives us a way to measure the actual distances to the lens and to the quasar. This is just the first level description. Let's dig deeper because it's not.
One thing that makes me think about it a little bit is it's like, okay, so an object, can you even count something that big as an object? This is like a little bit different hypothesis I was having, because part of what I'm thinking, I developed my own hypothesis on stuff. So is that, the third dimension, like maybe we don't even see the third dimension. I mean, Like, obviously, we think that we do, but it's like, what are we really saying? Light, and even the way they describe it's like light bouncing off of an object, or just light coming from an object, I guess, in the source of in the case of a quasar. But um, as far as reflective light, light bouncing off of stuff, um, and then we interpret that into stuff. But it's like, okay, are we actually seeing the atom? I mean, not really. The atom is absorbing light, and then it's re-emitting light. In the case of whatchamacallit, mm, reflective, seeing stuff or seeing objects or anything like that. And then as far as something that is creating, first of all, what's creating the photons, right? And of course the stars, but it's like gravity is sort of creating anyway. So if that light is coming from different places, and of course it's taking a different path because it's coming from different places, it gets really interesting, to say like, okay, are we really looking at the third dimension when we look at things at that scale, or are we now looking at the fourth dimension, which is why you can see something at different times? Just interesting to think about.
Not as easy as it sounds. First up, the actual math is based on Fermat's principle of least time. Light will always take the path between 2 points that takes the least time. This can be used to derive the bending of light by regular lenses, but it also applies to gravitational lenses. The paths taken in a gravitational lens represent local minima in the light travel time, paths for which the photon, if deviated slightly, would take longer to reach us. The path lengths give us one aspect of the time delay. The other is the Shapiro or gravitational time delay. Just passing through different parts of the galaxy's gravitational field leads to an additional time difference. The resulting time delay formula is surprisingly simple for such a complex system, and the most important thing about this expression is that the front term scales with the Hubble constant, with the expansion speed of the universe. That means the time delay goes straight to a Hubble constant measurement, and none of this depends on a chain of other distance measurements.
Interesting. It's an ad. That's interesting stuff. It seems like this is so far more about um, how to measure for um, gravity, the expansion, than it is about the expansion itself. But it's still coming up with some really interesting stuff. Um, just not exactly what I thought it was going to be about, but still very cool. Let's get back to it.
The standard for measuring cosmic expansion over the supernova method? Well, several reasons actually. One is the rarity of good gravitationally lensed quasars. These objects are rare already due to the precise alignment needed between observer, lens, and quasar, and most lensed quasars aren't actually great for this purpose due to the next issue, modelling the lens in galaxy. This is by far the biggest challenge. Galaxies make pretty terrible lenses compared to, say, precision ground glass lenses. They are lumpy, irregular objects made of stars and dark matter, and in order to properly calculate time delays, we need to know the gravitational field of that galaxy. It's kind of amazing that lens modelling is even possible. One particular trick is especially important. We can pretend that all of the galaxy's mass is collapsed into a flat plane due to the extreme distances involved compared to the size of the galaxy. This is the thin lens approximation, and it turns gravitational lensing into a classic geometric optics problem. So, we build a lens model based on the light of the lensing galaxy's stars and the positions of the lensed images themselves. That works pretty well when the lensing galaxy is simple. And that requirement for an easily modelable lens reduces the number of useful objects for time delay cosmography dramatically. But even in the case of a simple lens, there are confounding factors that we can't completely rule out. Even if we can see the light from the lens's stars, we can't see its dark matter, so we have to make some assumptions about how it's spread through the galaxy. We also have to try to model the gravitational effects of nearby objects like other galaxies. One of the trickiest issues is called the mass sheet degeneracy. We tend to assume that the lensing galaxy is the only significant source of bending for a given quasar's light, but that light is actually traveling billions of light years and may well pass through other gravitational fields, other mass sheets, on the way. It's very difficult to rule that out. These issues are best solved by making a different type of measurement of the lens's gravitational field. The stars of a galaxy move in the mutual gravity of each other, and it's possible to get a bead on that motion by looking for average Doppler shifts in their starlight. This lets us build a much less ambiguous map of the galaxy's gravitational field. But these sorts of kinematic measurements are very difficult to make, and typically only possible for relatively nearby lensing galaxies. Okay, so let's say we have a perfect lens model. How do we get time delays? Well, by monitoring the system for years with a decent-sized
This is kind of a new subject to me, by the way.
image in the lens. But
Sorry.
even building the light curve isn't easy. The separation between lens images is tiny, and they're often blended together when observed from the ground. They need to be pried apart with clever algorithms. That plus the faintness of these objects means that every measurement has an uncertainty attached to it. On top of that, we can't monitor continuously. There are gaps in the light curve during the day and during a long
If you ask me, you might have to just give up on this one, but no, I'm just joking. I might crack something else.
season gap every year when the sun gets in the way of our lens. All of this adds to the uncertainty in the time delay measurement when we try to line up the light curves from different quasar images. Combine the observing constraints with the lens model uncertainties, and we end up with some big error bars in our measurement of the time delay and in the resulting Hubble constant for any one lens. Okay, so where are we with this whole program? In 2019, the Holy Cow collaboration published their latest measurement of the Hubble constant based on the 6 best lensed quasars, getting a value of 73.3 plus or minus. And just last year, Holy Cow successor, TD Cosmo, improved the analysis and added 2 more lenses to get a slightly smaller 71.6. These numbers are more consistent with the late universe supernova value than the early universe CMB value, but the error bars are larger than the supernova uncertainties. Taken on their own, the time delay cosmography results don't confirm the tension between the late and early expansion measurements. But when these new results are actually combined with the supernova results, they actually do strengthen that tension and suggest a less than 1 in 10 million chance that these values are so different just due to random noise. But we're not quite there in confirming the Hubble tension. There could be some unknown systematic error that is pushing the supernova result to be higher than the CMB result. In that case, the lensing value on it.
Oh, so the supernova result is higher. I kind of would have predicted it to be the other way around. Though, I suppose if you have other forces, they might not be complementary. They could be dissonant, I guess.
Its own isn't tight enough to confirm the tension. Now, I'll come back to how that's soon going to change.
I actually think that there's something just like dark energy. I'll just say it out here. That is like dark energy, because if dark energy, in my hypothesis, exists between galaxies, right? Then maybe there's another energy that exists between superclusters. And I think maybe that's related to the eighth dimension. Just thinking crazy stuff. Let's keep going.
Imagine being able to build anything just by thinking about it.
That
Meet Base
pausing.
44.
First, though, quasars are awesome for this work because they are perhaps horrifically extremely abundant in the universe. But time delay cosmography was first conceived for use with supernovae.
I'm gonna have to look up this
how do
time delay
supernovae do it?
cosmography.
Well, precise measurement of time delay for the late fifth image of supernova Refsdal gave us a Hubble constant measurement of around 70, but with pretty large error bars. There's also the lens supernova CN Hope, which is extra special because it's the same sort of Type 1a supernova that are used to do our other late universe Hubble constant measurements. So in a sense, this one gave us two independent measures of the Hubble constant in one object. In practice, the two methods were combined. The lensing side gave us a fairly direct Hubble constant measurement, while the Type 1a supernova analysis allowed us to break some of the degeneracies in the lensing analysis. Hope yielded a Hubble constant that's also consistent with other modern universe expansion measurements, but again with huge error bars. For both of these supernovae, the error bars are large, but no larger than we get for any single quasar. The advantage of quasars is that we have more of them. Statistics lets us whittle down the uncertainty. In general, increasing the number of both lensed quasars and lensed supernovae is going to be the key to moving forward, and that is about to happen. In early 2026, the Vera Rubin Observatory will start its LSST survey, in which it'll image the entire southern sky every few days for a full 10 years. Combined with other new facilities like ESO's Euclid satellite, we expect to discover thousands of new lensed quasars and hundreds of lensed supernovae. It's been estimated that the Hubble constant uncertainty will be pushed down to around 1% or less, which, if it happens, will render the Hubble tension incontrovertible. But Rubin may be able to do a lot more. With enough lensed quasars and supernovae, we may be able to do more than measure the modern expansion rate. We may be able to trace the evolution of the expansion history over cosmic time. In the current cosmological model, lambda CDM, dark energy is assumed to have this constant density, but there's evidence that it's not the case, as I mentioned earlier. In 2025, the Dark Energy Spectroscopic Instrument team reported the results of its expansion history study using baryon acoustic oscillations, and we obviously covered that. When combined with the CMB and supernova results, DESI reports a strong indication that dark energy has weakened over cosmic time. This was the dark energy news of the decade. If we can measure that cosmic change somewhat accurately, we can actually start to nail down the physics of dark energy and figure out what the stuff actually is. Time delay cosmography with gravitational lensing may be the key to doing that.
That would kind of fit into a different aspect of one of my hypotheses that I don't really talk about. I think there might be infinite dimensions and they're constantly expanding. So if the dimensions themselves are expanding and there's new forces, though, in the 3,000s or the 3 billions of dimensions, they would be extremely weak, just like ridiculously weak, right? So a tiny little tug, kind of like slapping the ocean almost, once you get to those scales. But add that up with all the dimensions, that would be higher than the sixth dimension if dark energy is the sixth dimension. And then maybe it correlates. So that's kind of fascinating for me.
In fact, this could be the most important result that will come out of Rubin LSST, and many people are working on it. No big deal, really. We just clock the flickering echoes of 1,000 ancient cataclysms and discover the culprit behind our accelerating spacetime. Thank you to The Economist for supporting PBS. From reporting
Yes,
complex
indeed.
topics accessible and engaging,
Thank you.
geopolitics to technology.
Thank you, the Economist, and thank you guys for watching. This was another really really fun one. There's another one I want to watch on dark energy too, so I'm gonna go find that one because there was one that bridged entropy and dark energy, and I think entropy is the fourth dimension. Or no, gravity. Sorry, it was gravity and entropy that they were bridging. And I think gravity is maybe the fifth dimension, and entropy maybe the fourth. And so that sounds really fascinating. So I'm going to go look for that one too. In the meantime, hope to see you again. Be sure to like and subscribe, drop a comment, turn on the notifications. I truly hope to see you again soon. Bye, guys.